Every day, the world moves on as it always has. Cities wake up, work begins, and life feels familiar. But beneath that sense of normality, something is shifting. The climate is changing, and the systems we rely on, energy, food, water, cities, finance, are under pressure in ways we're only beginning to understand. These changes don't live in reports or projections, they are already shaping people, livelihoods, and communities. We created the Climate Leadership Podcast so these challenges don't remain abstract or distant, but are explored through the people working inside these systems, making real decisions with real consequences, often without clear answers. This is not a space for fear, blame, or perfection. It's a space for honest conversations about what leadership looks like in a changing world. If you're listening, you're already part of that leadership. Let's begin the conversation.
Welcome to another episode of the Climate Leadership Podcast, where we explore the real systems and scientific insights shaping climate action and decision making. Today's episode focuses on understanding climate variability and its growing impact on monsoon behavior and extreme heat in India. As climate risks intensify, the challenge is no longer just predicting but translating scientific insights into actionable strategies for resilience. Today, I'm joined by Mr. Rajib Chattopadhyay, Senior Scientist at the Indian Institute of Tropical Meteorology. With extensive experience in climate modeling and atmospheric science, he brings a deep perspective on how climate systems are evolving. Thank you, Rajib sir, for joining me today.
Yeah, thank you. And good afternoon, Amber. It's nice to talk to you in this topic. I look forward for the interesting discussion.
Thank you, sir. So, sir, before we start our conversation, can you please share with us a brief journey about your professional career so far?
Yeah, so basically, it's a journey of, I am in this profession, almost 15 to 20 years almost now. So I did my PhD in atmospheric and climate science at Pune University. Now it is known as Savitribai Phule Pune University.
Yes.
And then I did a 2-year postdoc in University of Miami. And then I came back to India for this job, which I got during 2012. So starting from my PhD, my research interest is looking into different kind of weather and climate systems, especially predictive aspects. So how to better predict those systems and those things. So working on one thing called subseasonal extended range prediction, which is prediction beyond 2 to 3 weeks. Okay, so when my PhD thesis was the extended range prediction, and that time there was no extended range prediction. So from the Ministry of Earth Sciences, this institute, we took an effort to understand the extended range prediction. How do we predict beyond weather scale? So weather scale prediction was very well known, and then there was predictions of seasonal scale, which is existing in India for say 100 years, more than 100 years. But extended range was very challenging. So we did some research that time, and I'm happy to share with you that our predictions, my thesis led to one of the important extended range prediction system right now existing. And a lot of development has happened in the last 15 to 20 years. And so that the systems like monsoon and the heat waves or cold waves and all those things has been predicted with. So the concepts evolve I am deeply connected with the evolving concepts of extended range prediction. And then that's how my interest in hazard and all these things started. But so 3-4 years back, I got a chance to work in IMD, India Meteorological Department. It's an operational agency where I came in touch with real operational people. From the theoretical background, I was working on science mainly. Then I when there I meet with people, and I meet with many journalists, and meet with many people who are working, and then I find out that these type of prediction system is one thing is scientific, the other part is the communicating these predictions to the stakeholders. So we need customizations of this information. So last 4 5 years I am working on these aspects, that from a pure scientific forecast, how it should be communicated to the people who are really requiring this forecast. Earlier it was like only for the government, but now it is like any stakeholders who are coming to us later. And also, I would like to say that in the last few years, I am working with AI-based models, which has come up a long way in helping us to connect to people with simpler versions of the scientific and technical jargons, and that is has been it. So this is in brief I want to say about myself.
Thank you, sir. It's really wonderful to join you today. And let's get started.
Yes.
So, to begin, how would you describe the current state of climate variability in India compared to a decade ago?
So see, I want to say one thing. There is perception. So there is one thing called weather and climate. So climate is the long-term statistical average. Okay, and weather is the what we see in the day-to-day. So if you break these things into decade-wise sense, the common perception is that the weather and climate weather patterns have been showing some extreme erratic variations. Okay, which has become localized systems are becoming much more like cloudbursts, for example, are becoming much more frequent. Okay, and for a decade or one or two ago, the heat waves were largely we are concerned during summer season or maybe May and June. Nowadays, warm weather, mild winters, high nighttime temperatures are very common year round. So these are now becoming sometimes longer durations and more frequent. So we hear more these events. Similarly, during the monsoons, the cloudburst, urban flooding, and high rainfalls, where like rainfalls over a city is occurring for a month's accumulated total in 1 or 2 days. So such situations are having much more common in terms of if you see the media reports and everything. So this is, I think, this is one of the most important change I am seeing. Even the statistical records of the IMD and other ways like which who are monitoring the long-term weather and climate, we are seeing changes like marine heat waves, for example, which earlier we did not thought about it. Now we are getting a lot of information about marine heat waves. Similarly, for example, Himalayas and other where which is showing some faster warming at the high altitudes. Okay, so these changes has forced everyone, scientists to the policymakers to the common people, to think in a very much holistic way. And I would say that this there is a sudden change that has happened. So that is no doubt.
Okay, sir. Nice. So, the Indian monsoon is often described as highly complex. What are the key drivers influencing its variability today?
Indian monsoon is a very large scale system. So when we started research, actually, if a model don't simulate monsoon, it is not considered to be a good model. Okay, so it is such a complex system. So basically, Indian monsoons we study monsoons in two ways. One is like we call it as the local factors; those influence the monsoon, and the remote factors. But how the basic monsoon flow forms? So monsoon, this is a seasonal reversal of wind, which is the famous flow which is coming from African region to the Indian region, the turning of the wind. So these winds are actually initially described as a giant land sea breeze system. So because of the solar movement, the continent got hotter and warmer, and because then there is low pressure area formed over this region, so winds are coming rushing towards it. So this is a like land and sea breeze which we see along the coastal region. So, but once it is established, these things like land down, okay, because rainfall occurs. So then, how it sustained for such a long term? So there are a lot of factors like local factors and global factors. Local factors, if we see oceanic factors like Bay of Bengal and Arabian Sea, these from here the monsoon systems are formed. The monsoon trough, which we see, is a low pressure region which is moving up and down slightly along the Indian continent. So, which give rise to lot of weather systems. So, from moisture laden air coming from the Bay of Bengal, and they form the rain bearing systems and then give rainfall. So, similarly, other factors like land surface temperature or land soil moistures, these are also some local factors. Vegetation covers, aerosols and pollutions, for example. These are some of the important local factors. The remote influence are also much famous because if you there's an interesting story that this story I want to just tell you that when we started seasonal forecast maybe around 1885, something around that time. So it was found that time that there is a strong relationship between rainfall over India and the sea surface temperature over Pacific region, or the it's other way that like the sea level pressure fluctuations between Darwin and Tahiti. So this is this fluctuation with the rainfall. So people did not knew about El Nino or so systematically. So these are the remote factors which has influenced the prediction of monsoon in the seasonal scale. Later, a lot of other factors like came from the North Pacific, okay, North Atlantic, okay. Now it is factors like very much warming in the Arctic, which is called Arctic amplification, like very strong warming. So which changes the temperature distribution from south to north. And ideally, the equatorial region should be more warmer because sun is directly over there, and then the poles are cooler. So if Arctic is warming, so the temperature difference is reducing actually. So that is a factor which nowadays people are studying very at length. So it is a complex system. It's the interplay of multiple factors from local to remote, which is controlling its rainfall amplitude, variability, year-to-year variations, extremes, for example. This is how it is.
Okay, sir. So, sir, are we observing a structural shift in monsoon patterns due to climate change, or is still within the natural variability range?
One thing I can say for sure that extremes has increased, and systems like the systems which give heavy rainfall is earlier there are. So the study is now more than first study is now 20 years old, which is a science paper where it was shown that the extremes are increasing and the low and moderate rainfall events are decreasing. So what is happening is even though the quantum of rainfall, like seasonal mean of rainfall, average rainfall is not changing that much, but the extremes are changing. So, so the change is occurring in how the rainfall is falling over the land. Now, these type of things are clearly linked with global warming, but it's a very difficult to say a particular event or particular system is formed due to global warming. So this is a very interesting paradigm. I always say that it's like loading a dice. So you have a dice like Ludo dice, which we play, and there are 6 faces. So if we have one face, it will fall one of the 6 answers. Okay, so either 1, 2, 3, 4, 5, 6. Now suppose we put some weight over one particular face. We know it from the story of Mahabharata actually. So that then one particular outcome is much more favored. So it is seen that the particular outcome is really favored, and many climate model experiments and those things indeed confirm this. But even if we have a fair dice and we have a loaded dice, both can give 6. So one particular incident, which is difficult to tell that if it is happened due to a fair process or fair, but statistically the number of events, the statistics are actually changing very rapidly. The other part of this problem is like huge land use, land cover changes, anthropogenic changes of environmental issues, environmental degradation, okay, due to urbanizations and all other things, which may not, even if there is no global warming also, suppose the warming is not there, but if we change the environment too much, it is going to change the rainfall type and pattern variability. So it's, event wise, we cannot be very sure that it has exceeded, because the IPCC and all those things, they still target 2040 as before that we should be acting. So but the evidence and the climate models, the mathematical models suggest that the things that we are seeing is consistent with a shift in the statistical shift in the rainfall event or distributions from one phase to another.
Right. Okay. So heat waves are becoming more frequent and intense. What are the primary scientific factors driving this trend?
Heat waves are actually, heat waves are actually temperatures fluctuations when they are going extremes. Okay. Now, scientifically speaking, there are a lot of different ways to quantify something as a heat wave. Okay, and when we say heat waves have increased or extremes, what you basically mean is a temperature fluctuations that is above our body or our human body can tolerate. Okay, so one thing is sure that this has earlier, if you have a lower temperature, or for example night are cooler, then we can take rest. Now day night temperature is not different that much, so then what happens is our metabolism is affected by that. So the factors that I see is recently, one we can see, of course, the has mean temperature has changed. Like there is a warming of the this thing. So one thing is ocean has warmed, land has warmed. Okay, so that's why you, even if the same temperature fluctuation you are seeing, suppose earlier it was 32 degree is the May temperature, mean temperature, and there is a 5 degree increase due to some factors. So then it goes 37 degree. Now, if the mean itself has changed to 35 degree, then if you add 5 degree to it, it crossed 40, which is 2 degree above the body temperature, 38 degree, which so even if the fluctuations are the same order, but because the mean has increased, then the temperature has become the feeling of the heat wave has increased. The other part is there are several studies which shows that there are global waves which actually there are many mechanisms. One is called the wave resonance mechanism. So two waves come together and they increase the amplitude, and those amplitudes stay over a region, and then amplitude of temperature that those causes heat waves. A very recent study we did, we find that this is an interesting combination, because over Bay of Bengal we have the ocean is much more warmer. So some region of the Bay of Bengal, if we add some additional temperature perturbation, these waves, global waves, those travel, which are, we called it as mid-latitude Rossby waves in the mid-latitudes. They travel, and then sometimes if they are descending over the Indian region, and if we put a perturbation over the Bay of Bengal, then these two systems interact together over Indian region, and they cause stronger anticyclone, which means that there is a stronger subsidence and cloud-free region for longer time. So such type of scenarios. So it's partly due to like waves which are perpetually traveling, and partly due to regional factors which are actually means increasing the intensity and the frequency of the heat waves.
Okay, sir. Okay. So, sir, how do climate models help predict extreme heat events, and how reliable are these forecasts today?
So climate models actually do predict so there are like climate models. You may earlier we used to, long before we have only statistical models. So there is we find out some predicted relationship. We use those predictors, and then we use statistical models to like earlier the rainfall forecast, IMD's rainfall forecast. Then after we develop the numerical models which are solving some differential equations, and then they give rise to this thing. So these models have continuously been increased and improved in the last 50, 60 years, and then they are giving these things. But it seems that these models, based on these models, I can now confidently say these extremes of fluctuations, actually, which can be day-to-day fluctuations or daily weather conditions, it can be predicted up to 1 week in advance. But very extreme situations, we can confidently tell about 2 to 3 days. Okay. And sometimes nowadays I'm seeing the new type of models like AI based models which are giving much more. So how do a prediction is good? It's not only I'm predicting from ahead, but also I'm predicting over much more smaller region. For example, we need to predict over cities, we need to predict over particular street. Okay, so nowadays the predictions up to 1 week, we can say good up to a state level, for example, or a few district clusters. We can. But with very high resolution models, informations we are now getting, 2 to 3 days we can say about, we can be, it is very good up to 2 to 3 days for village level, for example, or a city level. It is somewhat we can give some indications of those extremes. Okay, not always, like cloudbursts cannot be given like that, but at least heat waves, for heat waves it is a possibility now.
Okay, sir. Right. So, one of the biggest challenges in translating climate science into action, where do you see the gap between the scientific insight and policy implementation?
So when I started working, the biggest challenge was to give that I have a temperature of 38 degree. If my model gives a forecast of 38 degree, then it's a very good forecast. But slowly, it is understood that there is a limit of predictability. This information has to be, we cannot be predicting extremely well for a very large forecast window. So currently, this biggest scientific challenge is to convert this forecast of a numerical or a statistical or a mathematical model with add some socio-economic information and convert this forecast into a risk information. So mathematically, risk is now quantified by various studies. So depending on the user or a stakeholder, how do I provide the same forecast information, convert it to a risk information for a particular stakeholder? Okay, so that thing is right now challenging, and that thing is right now risk information we cannot able to communicate to the last mile. Okay, in spite we give warnings of these things, sometimes it happens that this information is not well focused or well customized. Okay, so this connection with society is required, and this has to improve. And this improvement requires like we need social scientists, we need people who are communicate, who can communicate these informations, but they do not miscommunicate also. So if we have information which should be scientifically correct, but it should not be providing any wrong message to the user. So we are so far successful. For example, in India, if you see, cyclone forecasting has become now an art, and IMD gives a very nice, precise cyclone related information to the user. So depending on that, nowadays we are also going into the heat wave forecast. For example, a lot of different methods have come out, and this. So still, I believe that communicating to the people over different region, India is a big country, and we have to communicate in regional language to the exact term that would give a feeling of that information. So this is, I believe, is a biggest challenge.
Okay, sir. So, sir, how can governments better integrate climate models output into long-term planning and risk management strategies?
So, like as I said, so there is a translation gap. So climate models generate information globally,
Mhm.
but that information has to be downscaled over city level or is village level, panchayat level, and those things can be done very easily nowadays through AI-based models, which we are doing it. And so I think these informations, if we do it more flexibly, this translation gap, we take care of these gaps. I think this should be very important advance in this direction. Then the other thing is like climate risk. Although we know that there is a climate risk, this concept of climate risk has to be embedded into a fiscal planning. For example, if a seasonal forecast is there, if seasonal forecast is related to certain level of risk, then this forecast of risk has changed because of some new information has been given, okay, or the system has changed. So such type of situations, we need to incorporate some flexibility that if the forecast information changes, the risk information also has to be modified accordingly and has to be communicated to the people. And the final thing is, as I am saying, that the sector specific action plan is required. Like, we have the heat action plan over Indian region. So those heat action plans are actually very much successful in converting this information to the policymakers. So we need to do much more heat action plans, risk analysis, vulnerability analysis, socio-economic tying up of the information with the different sectors. I think that is to be done actually.
Okay, sir. So, what role do early warning systems play in reducing the impact of heat wave and erratic monsoons?
Okay, so both this case early warning systems comes from it's a like a forecast system, but the forecast system in which the warning part is embedded. So the warning system can help people to policymaker to plan ahead, and also it can help to reduce the loss of life and property because it gives some time for disaster preparation. Okay, so this is true for both monsoon and heat wave warning. So early warning system is a very effective way of using the scientific information to the scientific communication, and that's how I think it helps. Okay, to a
Okay,
lot of people.
right, sir. So, from an economic and infrastructure perspective, which sectors in India are most vulnerable to these climate risks?
For me, this is my personal food security and water sectors are two important sectors for which require much more attention for specifically for heat wave risk and monsoon extreme risk.
Mhm.
Okay, the other thing I can immediately think is like coastal regions, like coastal ecosystem, because of the sea level rise and all other things,
Mhm.
and like cyclones, for example. So coastal regions actually very much vulnerable to this type of changes. The In terms of urban perspectives and all other things, I think labor intensive sectors like law studies have shown that construction,
Mhm.
unorganized sectors, and these guys are bound to suffer loss if such type of problem heat waves passes. If we do not modify how we are taking action,
Mhm.
this is going to be difficult.
Okay, sir. So, how can climate services be strengthened to better support decision makers at the national and regional level?
Uh, like uh, for me, it's like climate is always nowadays climate science has become an interdisciplinary subject. Okay,
Mhm.
so it requires participation from different sectors. So what specifically we used to generate like a pure mathematical number, now we require co-production of multiple type of informations. Okay, it's like we need to generate climate information, we need to generate the impact information, and all those informations are required to be generated. So for example, we can create these things through decision support system dashboard. Okay, and we create like in the financial sectors, physical risk and transition risk, we can create this type of informations for the national banks and all those things who are actually they are coming to us to get those type of informations. So another thing is, I think we should encourage more climate-based startups. Actually, those startups actually can design very innovative methods which are much suitable for a particular applications and these things. So they have to connect the climate information with the sector-specific information, and also this can be done with some. So these startups, I think. Supporting the startups, which is very important. And in this sense, I think that for better decision supports and all those sectors, we need a strong AI and large language model path to the climate information, so that it reaches to people, it reaches to different users, and all this. So I think this is how we can strengthen the decision makers actually.
Okay, sir. So, finally, looking ahead, what advancements in climate science and modeling give you the most optimism for improving resilience?
Well, as I am multiple times stressing that I believe that improving resilience is not only is a part of a climate forecast system, it's a part of a whole system of climate science and all other disciplines for which we are. So I see the problem is that this is a one part is that we are going to continuously develop the models, improve the model forecast, climate information forecast. Then at the same time, we need better models, for example, AI-based models, which are language-based model, which improves the regional projections or the local level projections. So also we need to improve the operational monitoring. So I think based on a real advanced monitoring system added to the forecast and then combine this information with the AI based and LLM models, I think this is the route in the near future, and this is going to help the climate related stakeholders in the long run.
Okay, sir. So, thank you for sharing such a clear and insightful perspective on evolving climate risk facing India. Today's conversation highlights that climate variability is not just a scientific challenge, but a critical input into economic planning, infrastructure resilience, and policy design. As monsoon uncertainty and extreme heat intensify, the ability to translate climate models into actionable decisions will define how effectively societies respond to risk. Bridging the gap between science and implementation will be essential for building long term resilience at scale. To our listeners, thank you for joining the Climate Leadership Podcast. Until next time, take care and have a nice day. Bye bye.